Hello, my name is Jonathan Dean, and I'm a junior biochemistry student and a Marquis Star Fellow working in the Petersen lab. This work was done under the mentorship of Dr. Kimberly Petersen, and the project is being led by Josh Frost. Before anything else, I want to start by defining some terms and concepts important to synthetic chemistry. Stereoisomers are molecules with the same structure and sequence of atoms, but they're arranged differently in space. They can have one or more stereocenters or points a central atom is attached to four different groups. This is connected to another important property called chirality. A molecule is chiral if it has a non-superimposable mirror images, called enantiomers. A good way to visualize this is your hands. Your hands have the same parts, but they're arranged differently. Being able to target a specific enantiomer or having enantioselectivity is very important for drug development, since the human body is a chiral environment. For example, camptothecin is an anti-cancer chemotherapy drug that contains a chiral lactone, shown highlighted in red. Lactones are key structural components in many bioactive compounds, and in this case are important to camptothecin having a biological effect. The active form of camptothecin is an S or left-handed enantiomer that targets a left-handed receptor. The right-handed enantiomer doesn't have any effect, similar to how your right hand doesn't fit properly in a left-handed glove. This is just one example of why it's important for researchers to be able to target a particular enantiomer. So the problem that we're seeking to address is that there's limited syntheses for chiral lactones. The basis for this project is the Pinner reaction, an acid-catalyzed reaction between a nitrile and an alcohol group, which can be used to produce a Pinner salt as a stepping stone in lactone synthesis. However, the reaction lacks stereoselectivity and uses harsh acidic conditions. Previously, the Petersen group has synthesized lactones from diesters in high yields and with high selectivity for one enantiomer, or desymmetrization reaction. In a similar line of work, previous research has involved the successful intermolecular cyclization of lactones, or the formation of a lactone ring, with a chiral center using the Pinner reaction under mild acid conditions. The goal for this current work is to develop a novel enantioselective Pinner reaction for lactone cyclization. It's been hypothesized that this can be achieved using a phenol or an OH on a carbon ring for the cyclization instead of the previous alcohol. If successful, this would provide a relatively simple and cost-effective route to synthesizing chiral lactones. Before the cyclization step, precursors of various functional groups, or R groups, have to be synthesized by first alkylating a dinitrile with a protected phenol, forming a new bond between the two compounds before deprotecting the phenol to produce the appropriate starting material. Moving into the synthetic work done so far, the main event of this reaction sequence is the alkylation and subsequent deprotection to the target precursor, marked as reactions 3 and 4, which first require the synthesis of starting materials, first being the dinitrile. Shown below are the two variable R groups used in the synthesis work I've done so far, a biphenyl group for R group A and a methyl group for R group B, with the dinitrile group being introduced by reacting with malonitrile, the details of which are not shown. Yields, or the amount of product I actually got out of what I theoretically could have gotten for these reactions, have varied without noticeable cause. Reactions 1 and 2 involve ocresol, which introduces the alcohol group. Reaction 1 involves protecting the alcohol, or basically putting a cap on it so it can't react, and then brominating it in reaction 2. The bromine is needed in order for the following alkylation reaction to occur. These reactions have been performed successfully 5 times, labeled trials A through E. The protection reaction has been relatively consistent in yields regardless of any differences in conditions, save the last reaction where there are some issues with purifying or isolating the compound after the reaction, and in reaction 1E, some product was lost, leading to a lower yield. The bromination reaction, on the other hand, has varied widely in its yields. Possible causes for this include trials 2C and 2D being on a double scale. However, it also seems that performing the bromination relatively soon after the protection reaction improves the yield. The alkylation reaction, or reaction 3, is where the two starting materials, that being the brominated ocresol and the dinitrile with the R group, are combined into a single compound. This reaction is the same regardless of the R group used. The alkylation reaction has also been variable in yields, with a third reaction with R group A standing out with almost doubled yield. I believe this to be a result in varying the temperature conditions, with the third reaction being left in an ice bath and allowed to warm to room temperature. However, it could also involve a carryover from the greater efficiency of reactions 1C and 2C. The deprotection of the alcohol, or reaction 4, has been attempted twice for the R group A version. The first being inconclusive due to the target compound mostly cyclizing during the reaction, while the second and third reactions successfully synthesized the product after running the reaction for a shorter period of time, but yields were relatively low. This NMR shown here is evidence that the target precursor was synthesized. as the two hot peaks corresponding to the methylene carbons highlighted A and B correspond to the non-cyclized product. As in the case of the cyclized product, which is shown in an overlay of the NMR, the peaks have a different chemical environment and are indistinguishable. One problem we encountered with this reaction is that the phenol is highly reactive and will cyclize to lactone almost on its own. These two overlaid NMRs are actually cases where the product was left on the bench top rather than being refrigerated, and it cyclized on its own overnight, no initiation needed. So this was a constant issue we ran into. Partially because of that and due to other factors, at this point in time, work with the pin reaction has been discontinued, so we will not be proceeding to the cyclization of the phenolic precursors. Looking forward, we'll be working to apply improvements made from this work to other projects. Personal takeaways for me include being introduced to basic synthetic chemistry. This was my first project work that I was working with. I also gained experience in troubleshooting reactions, particularly during the bromination reaction and the alkylation reaction steps. And I also learned the importance of time management and efficiency of my reactions, quickly following the bromination with the alkylation reaction into the deprotection reaction, seemed to improve my yields, and is something I'll be looking to apply to my future work. Thank you to the NIH for funding this research, and thank you to the Petersen Group and to the UNCG Marquis Star Program for their support, and thank you for viewing my presentation.